You can see the screen, right? So last time, I gave an assignment to compare the pipeline version and the parallel version. And I remember that one group actually explained about the ADP perspective, that if actually the runtime does not make any much difference, and it's actually very noisy. And the real problem is that the Vivado HLS reports somewhere around like nanoseconds, but actual runtime is around like milliseconds, which means that it's like 100 times slower. So why is that so? Like, why is it actually a lot slower than we expected? Why? It's because the DRAM is slow. The DRAM is very, very slow. So going back to the original von Neumann architecture, which is the modern computer architecture we use today, how it works is that initially the data is inside the DRAM. It's like this. And then whether it's even a CPU, GPU, or an accelerator or whatsoever, the data should be transferred to the CPU and do some computation and store it back. And this data transfer time is actually taking a lot more than we expected. And why? Because we are using a very bad interface called MAXI, which is also bottlenecked by eCPU. So to improve this, first we need a better DRAM, but we cannot do that because our board is fixed. So another option is that we use DMA, a better interface. And before we talk about DMAs, I would like to introduce a topic about arithmetic intensity. Have you ever heard about this concept on like a computer architecture course? So no? I think we actually did this in our course, no? No, I say, okay, so arithmetic intensity is defined as the number of operations per byte. So for example, let's say we are doing a vector add on like int integers. So each operand are bytes, and we have a plus b equals c. So we need 3 bytes of transfer, and we are doing 1 addition operation, meaning that the arithmetic intensity is 1/3. So what this tells us is that, I know this could be confusing, but let's try to understand this roofline model. So you see a straight line here. We say this is based on the peak performance, which we call it compute bound. Let's say our CPU is working on 1 gigahertz, and we have 1 ALU, meaning that we can do 1 addition per cycle. Then what's the peak performance? The peak performance is that 1 giga addition operations per second. This is the peak performance. We can do 1 giga additions per second. But the problem is that if the DRAM is not fast enough to fetch the memory you need, you will not achieve the peak performance you want. So let's go back to the vector add example. The vector add example, the arithmetic intensity is 1/3, which means that it's somewhere around here. So even though you want to compute the vector add, the memory, in cases where the memory is not fast enough, it will be bounded by the memory bandwidth. And that's why we are not utilizing the peak performance as we expected. You understand this? The main idea is that even though your hardware is super, super fast, if the DRAM is not fast enough, you cannot achieve the peak performance. And there's 2 reasons behind this. First is that the DRAM is slow, and second is that the application itself has a lower arithmetic intensity. There are applications that has more arithmetic intensity, such as convolution. In convolution, if you take 1 byte, you will do more than 2 or 3 operations, which means that it will be somewhere around here. In applications where you have higher arithmetic intensity, it is very likely to be compute bound. In that case, you don't have to worry about memory too much. But since we are doing vector add and saxpy operations, we are not utilizing the peak performance. So that's why today we are going to learn about DMA. And also, including the DMA stuff, we would like to talk about streaming architectures. So the reason I'm introducing about streaming architecture is that in the final project, you will be likely to make a fully working DNN accelerator. And if you ever succeed to make it with a streaming architecture, I'm pretty sure you'll be the number one, the fastest group. But in my experience, nobody actually succeeded in making a streaming architecture. But anyway, so what the hell is a streaming architecture? So we have used the pipeline version before, right? Meaning that in the very, very well-made pipeline version, all the memory stuff should be hidden with the compute latency because it's pipeline, right? But in normal von Neumann architectures, that is unlikely to happen because if you, let's say on CPU, you want to do the vector add example. And what you do is that you have some sort of like assembly code. You load A, load B, add, store, and you do this forever until it ends. But instead of doing this, because we can pipeline this, let's make a streaming architecture hardware. And instead of all this pseudocode, we just say, hey, I will just push a stream of vectors and you do your job. In this case, we expect that we can fully utilize, fully hide the memory latency. So we expect our design to be faster. Okay? Any questions? Any questions about the last assignment? Any questions about DMA, streaming architecture whatsoever? No? Really? So that we will going to learn it today. So streaming architecture normally means that we will send data as a FIFO. So instead of like having a lot of pseudocodes like add whatever, like add store compute, add compute store, add compute store, we will just say, hey, I will push you a tons of vectors and you do your job. So the biggest difference between streaming architecture and non-streaming architecture is that you program it differently. Instead of doing all this, we'll just tell you only the size, the base address, and it will do its job. Okay, yeah. So one of the biggest differences is that the programmer does not care about load and store instructions explicitly. We just tell the base address and the length of the vector, and it should do its job. And from the architecture's view, not the programmer's view, we expect our hardware to fully hide the memory latency by pipelining. So let's try it. Let's make it. Open up Vivado HLS. Today, we actually need to do a lot of coding, a lot of HLS coding, to be exact. This is our like fourth lecture, fourth lab. I believe everybody is kind of used to how to make a project, so I'll just like make one. Let's call it VAD DMA. And the function is kernel VAD, new file, DMA, DMA. and a test bench. And please do not forget to set the parts as our pink board. Okay, so let's just make a top function. So using DMA might be very confusing because unlike the previous interfaces, this time we need a custom data type called AXIT. So the Vivado AXIT okay, sorry about that. I think the link is like outdated. But anyway, so in Vivado HLS, we actually have a custom data type only for the DMA, which is the APAXIU format. So basically, in the DMA not only sends the data itself, but it has extra signals called like keep, last, and valid, and so on. If you remember the top diagram, when we are using the block level diagram, we had additional signals such as like address, ready, valid, and in case of DMA, we have more signaled, and most importantly, we need keep and last signals to actually use the DMA. So let's start by defining our custom type for our AXI DMA interface. So I'm pretty sure if you have usage on C, you know what type def means. So APAXIU 32111 AXI, and let's call it AXIT. This means that we are using a DMA with a data bit, 32-bit data, and 1 bit for the last signal. And the 111 is pretty much the default. They're related with the unaligned transfer and so, but we're not using fancy stuff, so we will just call it 111. So basically, this means that we will make a custom data type for DMA, which has a 32-bit data type. And you see, HLS allows us to use arbitrarily bit length integers. So the default C only support 8, 16, and 32 bits. But in HLS, you can use 4-bit or 5-bit or arbitrarily bit length data types. And in order to use that, you need to include more header functions. So this is the standard int. And other than that, we need to use the APAXI sdata.h, which allows us to use the AXI, DMA, and the HLS string so that we can use the DMA related stuff. So I will just like pop on APAXI sdata, yeah. Since we have defined this as our DMA type, I will just make it as AXI. A pointer, which should be an array, something like this. And please do not forget to add the header files. Include add DMA.h. Okay. So the progma for the DMA interface, HLS interface, AXIS, which is the AXI stream, and the port should be in one. And just like the MAXI example, because we need to do the co-simulation, I will just set the depth to like, I don't know, 128. Port out, something like this. And of course, the size will be vector size we were going to add. So let's make it an SAXI light. SAXI light, port size. Ah, everybody's here, great. So basically, the AXI T type is a C struct. The AXI T type, which is the AP AXI U type, is a struct. It's a struct which contains first the data, which is the actual data we're receiving from the DRAM. And then the things we need to look at is the last. Last should be 1. And 0 for everything else. And keep, so I'm not sure you remember, but if you see the Zing processing system, the DMA bit width is either 32 or 64 bits. And there are cases, let's say you're transferring int8 data, and the DMA bus width is 64 bits. Which means that if let's say you're transferring 48 bits of data, and the DMA bus width is 64 bits. And you'll be wasting the leftover 24 bits. And that's when we use the keep variable. The keep variable is byte indexed. So when the keep is 1111, it means that you have 4 bytes in 32 bits. And 1111 means that you'll be using all the 4 bytes. But in our case, since our data type is integers, which is 4 bytes, meaning that it is always aligned as 4 bytes. So in our case, it should be always 1111. If you don't understand, this should be 1111 by default. So if you want to use the AXIT, we actually need to make a function that typecasts the AXIT data type into the integer data type we are using. Let's call it the pop stream. So the pop stream will take a single AXIT element E. And then it should return an integer because we want to cast it as an integer. So what's the actual data we want to receive from the DMA? Well, of course, the E.data. I know this could be confusing, but implementing a DMA on HLS is very unstraightforward, but we have no other choice. I actually have no reason how to explain this, but let's just take this as granted. This is just what the official document says to do. Because we actually need some logic gates that reads the signals, this means that the AP uint 4 means a 4-bit unsigned integer. The 4 is the bit width of the custom integer type you're using. Integer, okay. Volatile AP uint 1. The last is a bool of 1 bit, something like this. And of course, since we have a pop stream which reads from the DMA stream, we also need a push stream that writes to the DMA stream. This is a function that passes an integer to an AXIT data type. And because in the AXIT data type, we should explicitly mention the last bit. So I will just make an int last operand here. And we create an element E. And the data should be the RET, which the value you want to push. And the E.T. This should be 1111 in binary. And if you understand sign numbers, you obviously know that -1 represents 1111 in unsigned integers. And then the last is actually depends on whether this is the last element or not. So is everybody familiar with ternary operators? So you may have not seen this syntax, but we usually hardware developers love this syntax. So last, yeah. Do you understand what this is? So in case you're not familiar with this kind of syntax, this basically means that if last is true, E.last equal 1, else E.last equal 0, the same thing. And of course, we return E. Okay? Oh, good question. But there's one problem. This is int. And this is AP uint 1. Yeah. I will upload the source code after the class because this DMA code is very, very buggy on Vivado. Please don't blame me. It's just that Vivado's fault. And if you're used to C, does everybody understand what an inline function is? So inline function means that in normal C programming, if you ever define a function as an inline function, it will not be actually written as a function, but it will just like act as the code block. And in case of Vivado HLS DMA, it is strongly suggested to use the HLS inline here. I don't know why, it's just like DMA thing. So I'll just add the pragma HLS inline. In reality, the pragma HLS inline means that even though it is a function, it will not treat it as an individual hardware block. Rather, it will be replicated as the same logic gates on your hardware. So normally, if the Vivado HLS encounters a new function, it will implement as a hardware block. but the Vivado HLS inline kind of prohibits that behavior. So I will just use the inline here. And also here. Okay. Seems to work. And it seems that we have type converters for the AXIT, so we can actually write the main function here. So do you remember that when we are using the MAXI, the Vivado HLS kind of complained that, oh, you cannot use a non-defined length of array. Do you remember that, right? In MAXI, we always need to tell the predefined size of the array. But the DMA, which actually has the last signal, it is not required to have a predefined size of array, which means that we can always put the arbitrary size array as an input and output. So you see int size, right? Unlike our previous assignment, our hardware actually has the ability to compute arbitrary size vector add, which is a nice feature, right? So what I'm gonna do is just create a for loop. Sorry. And let's say int, I don't know, let's call it C. C is the pop stream in 1i plus pop stream in 2i, something like this. And then, of course, you can just use the push stream to push the result into the out. So push stream C. What should be the last? Last is the if I equal to the size -1, which is the last element. It should be 1. Everything else should be 0. And the out I should be something like this. Let's make it the 8 pragma HLS. What do you want to put it here? What should be inside this pragma? Data flow, correct. So we made the most stupid and slowest possible working version of DMA vector add. Let's see if it works. Before we see if it works, we need to make a test bench. Before I make a test bench, let's just add the definition here. Oh my God, this is so confusing. We add dma.h into main. And I don't know, AXI T A. Let's set the define size 128. I don't know, size. We'll do the same for B and C. And one very awkward thing about this is that you need to initialize the test bench also as AXIT. So for int I equals 0 to I until size. Let's make a for loop. And AI dot data, I don't know, 1 by I, B, and AI. Don't forget to put the correct signals for the last and keep even in the test bench. So I'll just do the same thing. If I equal to the size minus 1, which is the last element. We'll just make it 0, 1, everything else 0. And I will do the same for B, B, and let's just make it as 2. And the kernel V at for A, B, and C. And C, I'm sorry? Oh, thanks. Thanks a lot. I almost mistaken. This should be like this, right? Thank you. And this should be something like I and CI data return 0. Let's run it. Go. And if you actually run the test C simulation, you will see very, very weird values. The reason for these weird values is that you remember that the beta field is actually a APU int32 type, which is not an integer. So please do not forget, cast this as an integer. Something like this. I'm explicitly showing you this because please do not in case you make mistakes, e.data is an APU int type, not an integer type. So before you print out the actual values, please do not remember to cast this as an integer. And then if you run it, yeah, you should see the correct values, please. Oh, yeah, great. So you see our test bench is getting messier than expected, a lot messier. So we don't want to print the values every time. So one trick is that I actually explained it to some people at the second lab, but basically the return 0 means that the test bench finished with no errors. So everything else than the value 0 will be treated as an error. So one quick trick is that instead of printing all the values, you can do something like, I don't know, let's make int ERR equal 0. ERR plus equal, let's say ci.data. If it's not same as 3 times I, which should be the correct output, we increase ERR. So this line means that whenever we have a wrong output for CI, which does not match the 3 plus I, we will increment ERR. And when ERR is not 0, it means that we're having a bad result. So this is just one trick when you're writing a test bench. From now on, we will just make some complex IP that does like matrix multiplication, convolution whatsoever. So this might be a quick fix to get rid of very messy outputs. But anyway, yeah, we finally have a DMA version of vector add. Let's see the analysis. Sorry, I need to run the synthesis. I made some error. I don't understand why. Let's see. What? 29. Oh, my mistake. Insert. What just happened? Yeah. Okay. If you ever run the analysis, you'll find out that the latency is like a question mark. Why is that so? Because in the synthesis report, we actually do not know the size of the array at the compilation time, right? So this is where you want to use the trip count pragma here. So basically what this happens is that if you have a like undetermined array at your IP, it is actually very hard to benchmark your design at this point. We don't know the latency, right? Because it depends on the size of the vector add. So Vivado HLS actually has a pretty neat feature called the trip count, which means that in the synthesis, I want to see the results of a size of a loop that takes like 124 iterations. So let me demonstrate this. Let me just demonstrate this. So we have this for loop here, and inside the for loop, we can add inside the for loop, in the for loop, we can add a pragma called HLS trip count. HLS loop trip counts. So this means that, hey, just imagine that this loop will run 1024 times. Assuming that, tell me the latency for this case. So let's run the synthesis again. Oh, and it tells us the latency in cycles. So let's see. We have 1024 elements, and we take 2049 cycles. Compute that. Okay, great. Can you make it better? So at this point, I would like to explain about, remember the arithmetic intensity I have explained at the start of the class? The vector add itself has low arithmetic intensity, which is why even though we use the parallel version of our hardware, the unroll, it does not benefit much. So what we like to do is that we want to make a streaming architecture where the data kind of flows from the input DMA and just automatically adds and goes to the upper stream. And for these kind of streaming architectures, from the hardware architecture view, which is basically a FIFO. You have a bunch of FIFO for the input and output data, and like right next to the FIFO, you have the addition and load and the store units. So let's see the analysis view right now. And there's just a single loop. It's just like, you remember something different compared to the MAXI. So if you remember that the MAXI, the IP should take care about the address. You remember that, right? If you look upon the schedule viewer on the MAXI version of vector add, it takes the base address and adds some like offsets to the base address, and it computes the read and write address and then loads it and do, but that's the MAXI. And you see in the DMA, we don't do that. Why? Because all the address and load and store is taken control by the DMA IP. This is the reason why we use a DMA IP. The IP is not, it's not the IP's job to take care of address and valid and like read and write signals. So you see in the loop, the only thing it does is that it just see the I variable, the incremental pointer, and just see if this is the last element or not, and just add them and send it to the like DMA. Well, and we want to make it better. How? We would like to use the HLS stream. So if you ever have used the C++, you should have used the IO stream, where you can use this kind of weird bracket to print and like print to the buffer. We can basically do the same thing on HLS. In order to do that, we actually need to make one more custom data type, which is the AXI stream. And type def HLS stream, and HLS stream, which is actually a stream of integers, which curl name stream is stream int. Okay, and let's modify our main kernel to use the HLS stream. So basically, our hardware does three things. It loads, computes, and stores. You can think of this as a very simple processor, a three-stage pipeline processor that does loads, compute, and store. Therefore, we will make three functions. First, we'll create a load input function that takes data from the DRAM, I mean the DMA, and converts it as the HLS stream. So you might be very confusing about the HLS stream, but this is basically a FIFO. In hardware's perspective, this should be implemented as a FIFO, first in, first out buffer. Please don't say that you know what a FIFO is, right? If you don't know what a FIFO is, I have no idea how to teach you. Okay, so static void load input. So this load input will take an AXI int array and convert it as a stream int array. And stream int pointer in stream, the stream, and int size. So this is basically a for loop. And what we're going to do is that in stream, so this is a stream, which means that we can use this weird curly bracket. And we can use the pop stream function we have just used, and in something like this. And of course, How would you like to use this trip count pragma? And of course, if you're clever enough, you will have the urge to add which one? What do you want to add here? Pipeline. Correct? Let's try to make the initiation interval 1. And if you have the load input, you should also have the store results. I'll just make it as the why is it complaining? Unused, okay. And AXIT out, we'll have out stream. And in size, we'll basically do the same, but here, what we're gonna do is out I, which is an AXIT array, you would like to use the push stream. And we also need to specifically write down the last, which is basically saying the I equal to the size minus 1. If it's true, then it's 0, 1, else 0, like this. Well, this is basically a Boolean value, so we can just write it as this, but anyway. And then oh, sorry, my bad. What just happened? Static void compute add like this and this. And like this in 2 out. Great, done. And in the compute add, what do? We do the same actually. But this time we actually do some computation. Out 3. Okay, seems to work. In the last assignment, we had the null version of vector add, where we had to make some C buffers to improve the performance. In that case, the C buffer is usually made as an SRAM array. In the case of FPGAs, it will make as a bunch of block RAMs. In the hardware's perspective, that's what we call the on-chip buffer, a scratch pad memory, or just a basic bunch of SRAMs. But if you create a variable as HLS stream, it is implemented as a FIFO. And that's why, if you want to use the HLS stream, we need to modify the main function to have some FIFO stream. I don't know what to call it, but I'll just say that it should make a FIFO. Let's use this. Oh, I should want to use the pragma data flow. And we'll do something like static HLS stream int. Actually, the cool thing about HLS is that you can actually name the streams. So this has nothing to do with the hardware implementation itself, but it helps you debugging the signals. You can just write down some string, such as this. Just you can name the string. Well, there's a fancy feature, optional feature. Okay, we made some FIFOs. And then let's just fill out using the load, compute, then store. What's the compute at? Oh, in one stream, in two stream, out stream, and size. Now what do we have? We have store results. Out stream and size. Okay, I think I have store results. It says that this is done with 0 errors. I think our design is working on the C level. If you want to see the actual values, oh, it's working. And let's run the synthesis. Okay, am I going too fast? Okay, I will just take some rest after this. Get rid of, how can I get rid of this? I will just show the source code in a few minutes. Let's see. Oh, so we are going to add 1024 elements, and it only takes 1031 cycles. Meaning that, can somebody tell me the throughput of this design? What's the throughput of this design? What's the throughput of this design? Throughput. Is my English bad? Okay, just kidding. What's the throughput of this design? Almost 1, right? We are processing almost 1 element per cycle, which is very good. If we go to the analysis, so you see that the throughput, 1 elements per cycle, means that we are almost perfectly hiding the memory latency by HLS stream. So the benefits of using DMA. First, our IP does not have to compute unnecessarily like address and like incremental pointers and so on. Only thing we should care is whether this is the last element or not. And secondly, because we have a bunch of FIFOs on our hardware design, it's actually fast. Meaning that we call this as the, we can hide the memory latency and it is almost perfectly pipelined. So I'm very happy to see this design. So as long as the memory latency is memory throughput is fast enough, we should probably get better performance. Okay, that's great. If you're curious about the schedule viewer, you can just look inside, but this is just like adding, very simple. So I will stop at this point. This where this sentence is there. Oh, I hate Vivado. Okay, so please try to run the code simulations yourself. I haven't run the code simulation yet. Try to synthesize it, see the results. You look at the schedule viewer, run some code simulations. And if you're done, please let me know. Any questions? Yes. Yes, I'm sorry. Can you speak a bit louder? Streamint. How do you import streamint? Oh, I think the streamint is on the HLS stream.h. And you're talking about this streamint, right? This is just a type def. This means that create a FIFO with the integer data type. Other questions? Oh, I'm getting hot. Oh. If you use the HLS stream, you should probably have an architecture. So DMA is a black box from the IP's perspective. But what the DMA does is that you basically have a FIFO, which is the in one stream, which is a FIFO. And the DMA will fill data. And there is a compute unit, which is basically an adder. And then you have another FIFO, and you have another DMA. We often call these kind of architectures a decoupled load and store, meaning that this compute unit doesn't care about like data read or write, whatever, but only when there's data ready in the FIFO, it just pops one and pushes here. Do you get it? So you see, the DMA and the adder and the output DMA, they does not explicitly like communicate each other about reading and writing, right? Yes. You should wait. You just wait. You just wait. Yeah. Ah, that's automatically synthesized by HLS. You can, however, explicitly add a FIFO IP using the top diagram. Okay, I guess everybody has done the synthesize. So first, before you export an IP, please do not forget to add this line. This will make your life easier. Please add this line, export the RTL, make the top diagram, and try to make a working version of Python. Okay? Am I clear? Great. Okay, so finish your top diagram and see if the Python pink is working, and you're free. So we don't have a core lecture next week. And the week after the next week is like midterm week, so we don't have a week course. So I will see you guys 3 weeks after. Okay? Okay, just announcement about homework assignments. So after this course, you will have 1 week to do the Lab4 assignment, which is make this XPy version in DMA, and you have to compare the runtime with the previous assignment using MAXI. And also this time you will notice that it is a lot faster than before, about 1,000 times faster than before. So we will require you, just like the FFT example, to compare the runtime with the CPU. Okay? And next week we will not have a lecture. Instead, we'll just give you an assignment. And the assignment for the next week is to make a IP that does matrix multiplication. And after 2 weeks, we'll meet again here, and we'll use the matrix multiplication IP to run actual DNNs. Are we clear? Okay. So team, whatever team, 74? I don't know, like you guys are free to go. Okay. Finish the top diagram. See if it's running using Python, and you can go home. Great.